Right, so the last part of ANOVA is one-way ANOVA with blocking. Okay, so we call it with blocking. Before this, we just talked about one-way ANOVA. So what is meant by one-way ANOVA with blocking? Okay, so I think it will be much better if I explain it in one examples. Yeah, I mean, if you go through these statements, it might be a bit hard. Okay, wait. Let me open the PDF file. Sorry for that. Um, Hold on, guys, because the PowerPoint slide it has missing symbols. Yeah, because this one is on iPad. Okay, let me see this one. Hold on, hold on. Okay, right. Can you see the screen now? I've changed from PowerPoint to PDF. You can
Yes.
see the screen? Okay. Right. So what is one-way ANOVA with blocking? Let me give you an example. Okay. So previously, um, what we have uh, what we have what we are analyzing before is like, let's say we have three samples, right? Sample 1, A, B, okay, let's say we have three samples, and this is A, B, and C, okay? Let's say we go into a specific example or situation. Okay, let's say I am analyzing um, um, apa ni, the height of students, the easy example, the height of student in faculty A, B, and C. Okay, so let's say before what we have done before, let's say we have a sample faculty A. I have, for example, the sample size is 20. Sample B, faculty B is N is 20 as well, and this is 20. C is also 20. Okay, so means that I am actually comparing sample A, sample B, and sample C, uh, and I consider all the data, right? I don't care about, like, okay, A, B, and C now are faculty. So the samples are students. So I don't care about whether the students are female, male, year 1, year 2, or year 3. I just take all the 20 of faculty A, 20 students of faculty B, and 20 students of faculty C, and I compare. And I find what's the mean for A. Previously, we talked about mean, right? When we are comparing the samples. Okay. So that is, it means that there is no blocking. In this example, there is no blocking because I don't divide the sample with any extra parameter. Okay, let's say now, let's say I want to apply what we call blocking in ANOVA. So what it means by blocking is that, okay, I'm still analyzing the difference. I mean, I'm still analyzing, let's say, the height of students from faculty A, the height of students from faculty B, and the height of students from faculty C. But now I put an extra um, parameter or factor. For example, so now we know that all of these samples consist of students, and I want to know what's the year 1, year 2, and year 3. Okay, throughout the samples, throughout the faculties. So the height, now we're talking, like, let's say this example are talking about height. I want to compare the height of students from faculty A, the height of student from year 1. Okay, year 1 across the samples. Year 1 for faculty A, year 1 for faculty B, and year 1 for faculty C. I don't want year 2 and year 3. So I introduce like a block. This is what we call block, okay? Block. So means that you put like a specific, another extra factor in order to make your data more specific, okay? And let's say year 2 is ni lah. So when I introduce like year 1, year 2, year 3, that is an example of block. Yeah. So instead of analyzing the whole samples, I put blocks. So that's, you know, you can see that it is more specific. So when I have the data at the end, let's say I have the data for the height of students for year 1 for all the faculties, yeah, and then year 2 and year 3, I have a more meaningful data compared to if let's say I just have a height comparison of height of students from faculty A, B, and C. You know, there's no much idea. I mean, what the data means. Okay, so apart from let's say year, just now is just an example year. I can also put like another type of example is like male, female. Okay, so how is the height of male students from faculty A compared to faculty B compared to faculty C? Male only. I'm not talking about females. Okay, so that is an example of blocking, whereby you introduce another another factor in order to make your data more specific. Okay, understand? Understand, guys? Faham? Okay, yes. Okay, so basically this is what is meant by blocking. Okay, I don't want to go through the definition or the terms one by one because it's quite hard for you to visualize then. Okay, so this is actually, so when you have the blocking, okay, so when you have the blocking means that for the ANOVA table, before this we only have we have the degree of freedom, we have this SS, right? And then this MS, and we have treatment only. We have errors, okay, within the columns. But now when we have the blocks, we have an additional row in the ANOVA table where you have to know what is the variation by blocks. And there is a degree for freedom for the blocks, which is a C is okay. Now, let's say what is C and R here? Let's say you have okay, this is sample. Can you see the sample? Wait, let me put it. If you want to visualize treatment and block, let's say just now we are talking about 3 samples, right? This is A, B, and C, and these are sample or treatment. Sample and treatment is the same, or group sometimes they call it. Sample and treatment is the same, but yeah, you have to know that sometimes I refer it to sample because we are talking about population, and in population there are samples, so it's like it's more relatable. Okay, so now let's say you have samples, right? So this is actually column. Each of this is column. Yeah? Each of the samples is column, because let's say you have the data over here. Let's say you have 5. Let's say 1, 2, 3, 4. Let's say 1, 2, 3, 4, 5. Okay, this is blocking. Bila you go through every of that, nampak ke? Do you see the table? This is blocking. So this is actually row. This is column. Each of that is column. I hope you know what column row means. Column is the vertical data or blocks, okay? And row, this is row lah, row. Each of this is row. And this is actually blocking. Okay, right. So so in this, when we talk about one-way ANOVA with blocking, so you come across a certain term like C. C is column. Okay, C is column, and R is here a row, the number of rows. Okay, so column. Okay, so the number of column here is actually the number of samples or the number of treatment. Number of treatment, because if you have 3 treatment, then you have 3 columns. Yeah, so that's why it's the number of treatment, and the number of rows is the one that refers to the blocking. So when you apply the blocking, you can apply certain levels of blocking. Like just now, I put like year 1, year 2, and year 3. So there are three levels, right? So the R should be 3. But if let's say I put like male and female, there are only 2, right? So the R is 2. The number of row is 2, two levels. So this one will refer to the number of levels of the blocking that you apply. Okay, so that is R. Okay, so now when we apply the blocking, you have to take note on the new terms used, C, R. So the degree of freedom for the treatment will be C minus 1. It's actually the same as before, but just here that we refer to C, which is the number of column or the number of treatment. Yeah. So if you have 3 samples, 3 treatments, 3 minus 1. Okay. So the blocks here, the degree of freedom is R minus 1, the number of row or the number of levels of blocking that you apply. So if let's say just now year 1, year 2, year 3, the R is 3. So the degree of freedom for the block is R minus 1 or 3 minus 1. And for the error, error of unexplained within columns. So within columns is within the samples actually. Why it is called error is because it's actually the replicates. Yeah, kalau kita ambil satu sampel ni, we just actually have many replicates, right? And we want to know like the variation between replicate 1, replicate 2, and replicate 3. Let's say in this, each of the samples, we are talking about every samples. So it's actually the variation between the replicates is the error. Okay, variation between replicates is called error. Okay, that's why it's called error. Yeah, variation between the replicates. Let's say you are taking samples from one area. Yeah? Let's say you are collecting certain species of animals, like maybe insects ke apa ke. You are not going to take only one, right? In any experiment, you are not going to do only one experiment. You have this kind of replication concepts. That's why you have duplicates. Duplicate at least lah. Replicates, triplicates. Triplicates means 3 replicates. Yeah, you must have more actually number of experiment in order to be convinced or in order to know whether or not your data are reliable. If you just collect, let's say, only one insect, let's say from Cebu, you take only one sample and you analyze that one. Are you going, I mean, if let's say the audience, let's say you are the audience, are you going to believe any experiment or conclusion made from only one experiment? Of course, no, right? So that's why you have to have more replicates in order to know that if let's say the pattern is the same from one replicates to another, or maybe the error is very little. Of course, there is a variation, but if the error is little, it means that the result is consistent. The result is consistent. It means that you are convinced with the data. So that is actually the replication. But the variation between replicates tu adalah error. Okay, so that's why this one is called error. Within the column, within the sample. Yeah, within the column is within the sample over here. So this is the formula given for the error. Okay, and the same thing, you would have the sum of squares. Before this, we have SST for the treatment. You would have for the error, for the blocks SSB, we call it, for the error here SSE, and for the mean of squares, MST for the treatment, MSB for the blocks, and MSE for the error. And for the F values, you would have 2 values of F. when you introduce the blocks. First is the F for the treatment, and the second is F for the blocks. Yeah. So for the treatment is MST divided by MSE. MSE is the same for both. I mean, you divide with MSE. For the blocks, the F is MSB divided by MSE. So you would have two values of F, okay, when you introduce the blocks, right? Okay, let's say this is an example of a problem with blocking, okay? So how you want to know which one, like this one is quite actually confusing, not confusing, it's like you have to decide by yourself which one is samples, which one is blocks, which one is treatment, which one is blocks. Let's say it's not given the word treatment over here, okay? You have to analyze from the question. I don't have the question over here, but you have to analyze the question, because the question will actually first, the primary aim of the statistical analysis is to compare the samples first, and after that you are comparing the blocks, okay? Like for example, in the case of faculty, just now I gave you the example of measuring or comparing the heights of students across the faculties. So the main aim, or what the first aim, is to compare between the samples, sample A, B, and C. The second aim, or the second target, is to compare in terms of the block, like let's say year 1, year 2, year 3. Okay, so that is the thing that you have to identify in order to know which one is actually the samples. Because you might got confused, like this one, you can say this one is also a sample or treatment, but actually it's not, okay? So you can also say that all year 1 are samples, but if let's say the aim is to analyze the faculty first, so your assumption is wrong. Yeah, so that's why you have first to identify which one is actually the samples. Yeah, so which one is the samples? So only then you can identify this is the samples. This is the samples, right? And this is the samples. And this one is actually the blocks. Okay, why that one is important? Because that will determine the calculation of the F values, because the MSB depends on the degree of freedom, the MST also. So all of those will determine the final values. So what you have to analyze here, if you are given these kind of things, okay, just go directly to the table here. Okay, this is the thing that you have to fill in, which is the same like the ANOVA before, but you have this additional stuff, this B, right? These blocks, because you have blocks. So at the end, you have to calculate the F for the blocks and also the F for the treatment, okay? And what you have to do with this F calculated, you have to compare with the critical F values. So it means that you have to determine also two critical F values, one for the treatment and one for the block. And how you determine that? Okay, so when you calculate the F from the table, this one is the degree of freedom, right? And this one is referring to the degree of freedom for the treatment, and this one is degree of freedom for the error. Okay, the error is always the second one for both of it. This one is for the error as well, and this one is for the block. And this one is for the treatment. So that's how you got the F value. And this one is 95%, so you have to refer to the 5% punya row in the table. Okay, so it means that you would have two critical F values, where you will compare those values with the calculated values. So you compare like the critical F value for the treatment 4.46. You compare this one with this one only lah. Okay, you have to match it correctly as well. This one with this one. Okay, so which one is depends on the rule of thumb, right? The rule of thumb, if let's say the F calculated is less than this, both of these are less than the critical F, it means that you accept the null hypothesis for both. So in your conclusion, you would have two conclusions. Two conclusions. One is for the treatment and one is for the block. So for the treatment, because both of them are less, you both of situations you accept the null. So accept null means that there is no difference, right, between all the samples. The fertilizer here are the treatment, yeah. And for the second conclusion is also no difference because you accept the null as well for the blocks. So now for the blocks, you are comparing the plots. So it means that there is no difference between the yield of the plots. Okay, so those are the things that you have to conclude. Yeah? So two conclusions for ANOVA with blocking. Yeah? Okay. So what is actually, why, when you have the blocks, what is actually the importance of it? It is important because we want to know the interaction. This is what we call interaction. So when the when the blocks and the treatments intersect, so you will know what is the interaction. Interaction means if you imagine just now the sample A, B, and C again, and then we have let's say year 1, year 2, year 3. So interaction means like what is the year 1 for all, what is the year 2 for all. I mean like across factor 1. That is this is what we call interaction, when the two factors meet, when the two factors coincide. Okay, so that is the importance of blocking. Okay, treatments and blocks are referred to as factors. Okay, so actually one-way ANOVA with blocking is also known as two-way ANOVA because both of treatment and blocks are considered as factors. Yeah, so one-way ANOVA, the reason why we say one-way ANOVA before is we are analyzing only one factor. If we are comparing the height, we are just comparing the height of sample A, B, and C. Yeah, so the height is the factor. But when we compare, let's say, the year of studies, right, and the height of the students, so the year is another factor. So the year is the second factor and the height is the first factor. So that's why there are two factors when blocking is introduced for one-way ANOVA. One and two-way analysis can be extended to multi-factor situation, but it will be more complex. The number will be more crunching. Okay, so that is for you to know. And this is actually just to introduce you the blocking. Perhaps we might not be asking you that really much, yeah, but you just have to understand what is blocking. Okay, so it's very short for this one. So just to wrap up the blocking lecture here, blocking means the addition of a new factor across another factor. Okay, so you mean like you introduce another factor. One-way ANOVA with blocking is also known as two-way ANOVA because two factors are involved. So what is the difference between one-way ANOVA and one-way ANOVA with blocking? You extend the ANOVA table by introducing another row for the degree of freedom, for the sum of squares, and for the mean of squares for the block. Okay, and there will be two values of F to be calculated, one for the treatment and one for the block. And also there will be two critical F values to be determined from F table, one for the treatment, one for the block. And you have to compare the F calculated for the treatment with the F critical for the treatment. I mean, you have to match it, you have to compare it correctly, like not to compare it wrongly, okay? So at the end, you have to make two conclusions, whereby one is for the treatment and one for the block. Okay, is there any significant difference for the treatment or for the samples, and also whether there is a significant difference or not for the blocks. Okay, So that is the one-way ANOVA with